October 3rd, 1993, the streets of Mogadishu. For 40 years, the narrative surrounding the downing of Super 61, a Sikorsky UH-60 Black Hawk, has focused almost entirely on the explosive yield of a Soviet-era RPG-7. But that is only half the story. The truth, buried deep within declassified engineering failure analyses, is far more terrifying. The Black Hawk was not just defeated by an enemy warhead. It was torn apart from the inside out by an invisible assassin. A lethal mechanical trap, a phenomenon known as harmonic resonance, hiding in plain sight at exactly 1,190 revolutions per minute. Let us strip away the mythology and look at the raw physics. I am going to peel back the 2024 T3 aluminum alloy skin of this tail boom to expose the central nervous system of this $60 million machine. Watch closely as we render the outer shell completely transparent. What you are looking at is the drivetrain. Up front, twin General Electric T700-GE-701C turboshaft engines generate a combined output of 3,240 shaft horsepower. That immense kinetic energy has to go somewhere. A massive portion of it is sent down this spine. We are looking at a segmented driveshaft spanning the entire length of the tail, composed of 6 individual hollow aluminum sections. These sections are coupled together by viscous damper bearings, ultimately feeding rotational force into the tail rotor gearbox. Now look at the tail rotor itself. The engineers at Sikorsky built this component to be an absolute fortress. The rotor blades are forged from a Kevlar composite matrix, featuring a titanium leading edge. They over-engineered it specifically to withstand a direct hit from a 23mm anti-aircraft shell. It is a masterpiece of ballistic survivability. But here's the fatal irony. In their pursuit of armor and material strength, they created a system completely vulnerable to the laws of acoustic physics. To understand this flaw, we have to pause the rotor and analyze the baseline frequencies of the airframe. Everything in the physical universe has a natural frequency. If you strike a tuning fork, it vibrates at a specific, unchanging rate. The UH-60's tail boom is a massive tuning fork made of aluminum and steel. Through extensive stress testing, engineers knew the natural resonant frequency of this tail section. Under normal combat conditions, the drivetrain spins at a nominal rate, pushing the tail rotor to hundreds of revolutions per minute, well outside the danger zone. The acoustic waves generated by the spinning shaft pass harmlessly through the metal frame. But the blueprints reveal a microscopic gap in this perfection. There is a very specific rotational speed, exactly 1,190 revolutions per minute, where the spinning frequency of the driveshaft perfectly matches the natural resonant frequency of the tail boom. If the driveshaft RPM drops and holds at that exact number, the physical vibrations do not cancel out. They synchronize. They stack on top of each other. This is harmonic resonance. It is the exact same physical principle that allows a trained soprano to shatter a crystal glass with her voice. Except, in this scenario, the glass is a military helicopter carrying highly trained operatives, and the voice is a 3,000 horsepower mechanical scream. The system is fundamentally designed to tear itself apart if it hits that acoustic sweet spot. And in the thin, searing 40°C air of Mogadishu, all it took was 15 grams of missing mass to trigger the countdown. Let us zoom in further on those viscous damper bearings connecting the 6 driveshaft segments. These are not simple ball bearings. They are filled with a highly specialized silicone fluid, designed to absorb the microscopic tremors generated by the twin turbines. We are taking a cross-section of the bearing housing. Notice the tight tolerances, less than 0.003 of an inch of clearance between the spinning shaft and the stationary race. When operating at peak efficiency, the fluid creates a hydrodynamic wedge, literally floating the driveshaft on a microscopic layer of liquid. But this fluid is highly sensitive to thermal overload. If the shaft begins to wobble, the friction spikes. The internal temperature of the bearing housing can skyrocket from an ambient 90 degrees to over 400 degrees Fahrenheit in a matter of seconds. The silicone fluid breaks down, losing its viscosity. The hydrodynamic wedge collapses. Metal begins to grind directly against metal. Now, look back at the tail rotor blades. They span 9 feet in diameter, acting as a massive gyroscope at the rear of the aircraft. They are pitched at precisely calculated angles to generate anti-torque, counteracting the immense twisting force of the main rotor. Every single ounce of weight on those blades is balanced dynamically. If you add or remove even a fraction of an ounce, you introduce a mass imbalance. Imagine taking your car down the highway with a heavy lead weight taped to one side of a tire. The steering wheel shakes violently. Now multiply that rotational speed by 10, and imagine that tire is attached to a hollow aluminum tube suspended 50 feet in the air. That is the kinetic reality of a compromised tail rotor. The Sikorsky design team knew about the dangers of vibration. They installed elaborate elastomeric bearings in the main rotor hub. These are essentially high-tech rubber shock absorbers, incredibly efficient at soaking up the brutal, low-frequency thumping of the massive main blades cutting through the air. However, by isolating the main cabin so effectively, they inadvertently created a trap. The kinetic energy, the raw, unfiltered vibration from a damaged tail rotor, has nowhere to go. It cannot travel forward into the heavily damped main cabin. So, it reflects backwards. It bounces off the elastomeric barrier and is forced straight back down the tail boom. The tail section becomes a rigid lever, amplifying the destructive force. Every single rivet holding the aluminum skin together is subjected to extreme shear stress. The 2024 T3 aluminum alloy is fantastic for its strength-to-weight ratio, but it is notoriously susceptible to high cycle fatigue. When you subject it to a constant, high-frequency, high-amplitude vibration, microscopic fractures begin to form at the crystalline level of the metal. We are looking at a simulation of these microfractures spreading across a rivet hole, expanding at a rate of millimeters per second. This is the anatomical layout of the hidden trap. A Kevlar-reinforced tail rotor, completely capable of surviving a localized explosion, bolted to a driveshaft system that will obliterate itself if forced into the 1,190 revolutions per minute death zone. All the enemy needed to do was scratch the surface. They did not need to blow the helicopter out of the sky. They just needed to alter its physical weight by a few grams, force the engines to bleed off speed, and let the unforgiving laws of acoustic physics finish the job. This is not just a vulnerability. It is a mathematical certainty, hard-coded into the very geometry of the airframe. Let us place this meticulously designed machine into the unforgiving crucible of urban combat. The airspace above Mogadishu is saturated with hostile fire. The trajectory of a Soviet-manufactured RPG-7 warhead intersects with the rotational arc of the Black Hawk's tail section. However, the initial kinetic impact does not trigger a catastrophic high-explosive detonation. The ballistic tolerance of the Kevlar composite matrix actually performs exactly as Sikorsky engineers intended, absorbing the blunt force trauma and preventing the blade from instantly shattering. But the kinetic energy transfer shears off a jagged, seemingly insignificant chunk of the blade's trailing edge. We are talking about a microscopic loss of mass. Precisely 15 grams of composite material vanishing from an aerodynamic surface that is currently spinning at 1,400 revolutions per minute. Instantly, the flawless gyroscopic balance of the tail assembly is violently compromised. The tail rotor ceases to be a precision, stabilizing instrument and instantly transforms into a massive, unbalanced wrecking ball attached to the rear of the aircraft. A 20G static shockwave, a burst of pure kinetic displacement, rips through the cast magnesium housing of the tail rotor gearbox. Inside the cockpit, the pilots are fighting a sudden, violent yaw. To maintain altitude and directional control, they instinctively and aggressively manipulate the collective pitch lever, demanding maximum available torque from the twin T700 turboshaft engines. This sudden, extreme power demand causes a momentary, yet physically fatal, bleed-off in overall rotor speed. Watch the digital tachometer telemetry stream drop in real time, from the nominal 1,350 revolutions per minute down to 1,280. And then it hits the acoustic death zone, 1,190 revolutions per minute. This is the exact millisecond the spinning frequency of the segmented aluminum driveshaft mathematically synchronizes with the natural resonant frequency of the entire aluminum and steel tail boom structure. The physical vibrations traveling down the spine of the aircraft no longer dissipate into the surrounding air. They synchronize. They stack. They multiply exponentially through the principle of harmonic resonance. The amplitude of the oscillation inside the hollow tail boom spikes brutally. What was once a safely engineered half-inch operational deviation instantly magnifies into a structural tearing 4 inches of lateral movement. We are now switching the visual feed to an internal, microscopic X-ray view of the primary titanium pitch horn. This critical component is directly responsible for altering the angle of attack of the tail blades. Under the grip of synchronized harmonic resonance, this titanium forging is subjected to an unbearable high-cycle fatigue load. The tensile strength of aerospace-grade titanium is legendary, but right now, it is being pushed far past its ultimate yield point by acoustic geometry. In real time, you can see the microscopic crystalline structure of the metal physically separating. The high-frequency vibration is generating intense localized friction, superheating the titanium at the fracture point. It takes exactly 14 seconds from the moment of synchronization for the structural integrity to completely fail. Let us track the failure cascade back up the tail. The silicone dampening fluid inside the viscous bearings, which we examined earlier, literally boils off. The vital hydrodynamic wedge collapses into vapor. Deprived of all lubrication and vibrating violently at the exact resonant frequency of its housing, the number 4 driveshaft segment succumbs to its own centrifugal force. It bows outward, scraping aggressively against the inner wall of the tail boom, generating a blinding shower of white-hot titanium and aluminum sparks. The immense twisting torque of the engines meets the acoustic resistance of the frame, and the drive shaft violently snaps into 3 jagged, distinct pieces. The mechanical link between the turboshaft engines and the anti-torque tail rotor is now completely and permanently severed. As the tail mechanism fails, the airframe instantly loses all anti-torque stabilization. The massive rotational inertia of the main rotor immediately transfers a counter-rotational force to the fuselage. The Black Hawk enters a violent, uncontrolled flat spin, rotating at over 120 degrees per second. The centrifugal force inside the cabin pins the operators to the bulkheads, exposing them to sustained multi-G physical trauma. But the internal mechanical destruction is still not over. Remember the elaborate elastomeric bearings located in the main rotor hub? Those high-tech rubber shock absorbers designed to protect the crew? They continue to perform their job flawlessly, preventing the violent, tearing vibrations from entering the main cabin. But by acting as an impenetrable acoustic wall, they inadvertently force every single ounce of that chaotic, rebounding kinetic energy straight back down into the compromised tail section. The tail boom becomes a rigid lever, amplifying the destructive force with every rotation of the main blades. The 2024 T3 aluminum skin buckles under the immense shear stress. The acoustic pressure waves decapitate the structural aircraft rivets, popping them out of their sockets like high-velocity shotgun pellets. The entire tail section, fighting a losing battle against the massive anti-torque twisting force of the main rotor and its own internal, amplified acoustic resonance, simply folds in on itself. The structural spars snap, and the tail detaches completely from the fuselage, sending the $6 million machine into an unrecoverable kinetic impact with the desert floor. This is the brutal, unforgiving reality of aerospace engineering. You can build a machine capable of surviving direct 23mm anti-aircraft fire. You can wrap it in state-of-the-art Kevlar composite armor and power it with over 3,000 horsepower. But you cannot armor a helicopter against the fundamental, invisible laws of acoustic physics. A mere 15-gram mass imbalance, combined with a highly specific rotational frequency, turned the Black Hawk's own immense kinetic energy into the exact weapon that brought it down. Welcome to DEFUNCT, the only channel where we dissect the catastrophic engineering failures that military history tried to bury. If you want to survive the next deep dive mechanical teardown, make sure to hit that subscribe button and engage the notification bell. You will not want to miss the machine we are putting under the X-ray next week. We are extracting the classified Cold War telemetry data from a Soviet-era nuclear attack submarine to expose a microscopic pressure hull design flaw. A flaw that turned a routine deep dive structural test into a highly classified instant kinetic implosion. See you in the next analysis.